this afternoon's session on why you should not trust interpretations in machine learning with Dr. Fei Huang. Fei is a senior lecturer in risk and actuarial studies at the University of New South Wales. Her research focuses on the explanation and fairness of insurance pricing using statistical machine learning methods and ethical and data science for insurance. She collaborates with industry to incorporate contemporary industry challenges into the course syllabus via sandbox projects for her students. And I think you'll agree there is no bigger contemporary industry challenge at the moment than AI and machine learning. I encourage you throughout the presentation and afterwards to enter your Q&As via the messaging, the Q&A function on the app. And on that note, I will pass straight over to Fei.
Thank you, everyone. Thank you, Kirsty, for chairing this session, the kind introduction. Hello, everyone. Thank you for coming to this session. We are in a very big room. It's very dark, but I do hope that we can have some more closer interactions. If you want to sit at the front, please feel free to do so. Sorry, accidentally click on this. So in this year's Actuaries Summit, I think we have heard lots of talks, lots of speakers talking about the importance of empowering AI and also the power of AI. But do you think there's something still missing there? You may be working in different areas, maybe financial services, governments, or different industries. Do you think you can immediately use AI in any of your applications? Is there any risks? Is there any constraints? Right. On the one hand, I absolutely echo that everyone should look at how can you utilize AI to boost your business. But on the other hand, I also want to remind everyone that there's a cost behind it. And one of the costs is the potential risks and interpretation concerns embedded in those black box machine learning AI models. So in today's talk, I would like to highlight, uncover the vulnerabilities of the AI and the machine learning tools, so that next time when you try to use that in your business, you have better understanding of what kinds of application can you use those AI tools, and what are the limitations behind it that helps you to better build up your business or communicate with your customers. So this talk is based on a paper that is already available on the Actuaries Summit website. It's called Why You Should Not Trust Interpretations in Machine Learning. And so in this case, we present you with a specific case study adversarial attacks on one of the very popular machine learning tools, partial dependence plots. But this is readily generalized. We can readily generalize this to many other interpretation tools. And I would also like to acknowledge that this work is based on close collaboration with two co-authors of this paper. The first one is Xi Xin, a PhD student from USW. He was a very hardworking, diligent student. I would like to acknowledge his extensive contribution in this work. And also the second one is Giles Hooker, who is a professor in data science, statistics, who have been doing interpretable machine learning related topics for 20 years. And he's currently a professor in the Wharton School of University of Pennsylvania. Okay, now let's give you a motivation of today's topic. AI is a word that everyone talking about today. So we know that the adoption of the AI techniques have been transforming our industry. And everyone should understand that there are lots of benefits embedded in AI tools. So most of us already know that how good AI could potentially transform your business, like it can enhance the efficiency, improve your accuracy. But today, I want to warn you that there are some risks behind it. For example, there's a lack of transparency and interpretability. So today's talk will specifically focus on this. But there can be other risks. And tomorrow I have another talk on the fairness issue. So you're also welcome to listen to the potential risks from the fairness perspective. Now, talking about interpretation, why do we need interpretation? You probably work in different industries, but do you have a need to communicate your results to your customers, regulators, or maybe your colleagues, your managers? Do you have that need? If you do, then please be careful of using any of those AI tools techniques, especially if you are in high-stake decision-making. By saying high-stake, it's usually related to, say, financial services, healthcare, criminal justice, those very important decision-makings. But if you do have some lower-stake decision-makings that does not impact people's life significantly, then there's lower risks associated with the AI tools. So in terms of interpretation, here we can give you some examples, for example, such as understand the feature importance. Do you need to tell your stakeholders which feature is most important to determine this business outcome? Do you have a need to communicate that how the model inputs leads to the model outputs? Or do you have a need to visualize the interaction effects among different predictors? Or do you have a need to understand the causal relationship? Is that factor really cause outcome or just a spurious correlation? If you do have those needs, then please be careful of using any of the machine learning tools. Another layer is the fairness. So in order to make sure that our outcome is fair, you must need the interpretation, because otherwise, how can you know, if you don't know how the model works, how can you ensure the fairness? A third layer is privacy. Lots of the privacy regulation require that certain protected attributes are not allowed to be used in your model. But if you cannot even interpret that, how can you ensure that those information is not used? And also, as a modeler, even if you are doing low-stake decision-making, as a modeler, you may want to have some guarantee that the model is learning the right signal, not the noise. Right? So that's interpretation give you a layer of validate your model and do some robustness checks. So now you probably say, hey, we agree that interpretation is very important. Then what kinds of tools can we use? The list of the tools here shown on the slides give you the readily available tools on the shelf that you can pick up to satisfy your needs. Let me briefly introduce each group of them. The first group, which I call partially interpretable transparent model. This group is many of us are already familiar with. That's our traditional models. So if you're a general insurer, you probably have been using GLM for ages. And GLM4 in this category, or other examples include linear regression, tree-based models. We call them partially interpretable because they are relatively simple. So they have a very simple model structure, have fewer parameters. So as a human being, it's easier for us to understand what's happening there. So that's why we call it partially interpretable. But we have a partially in the brackets because no models are perfect in terms of interpretation. In the ideal world, what we want to understand is a complete understanding of the interactions, the high-dimensional relationship among all predictors. But usually, we can only understand partially. So no model can do a perfect interpretation job. But some of the models are inherently partially interpretable. That's the traditional statistical models, because they are simple. Well, now we are talking about AI and machine learning, right? So these type of models are usually more complex, and we usually call it black box. We call it black box not because it's stored in a black box. Oh, sorry. It's because it's too complex to understand. So that's why we call it a black box. Actually, we can certainly understand if we have the capacity. For example, for a neural network, you could have 100 layers, thousands of neurons, millions of weights. How can a human being understand such a complex structure? That's why we call it black box. So, but this complex structure is very good at analyzing and predicting unstructured data or complex big data sets. So as a practitioner, especially in certain areas like computer vision, large language processing, these models can do a much better job than those simple statistical models because their complex structure can better capture the data patterns. So this poses another question. if you are working in the industry that really needs interpretation, and also you are working with high-end structured data sets, can you trust those machine learning models? And I just present you here, we know that we have a list of interpretation tools. Some of them are partially interpretable. For the others, you can see I classify them into two categories: global model agnostic methods or local model agnostic methods. So these two groups are for machine learning black box models. So if you're using black box models, you want to have some interpretation, understanding how the inputs are impacting the outputs, you can still use these tools. People have been developing even more tools nowadays. At least some of the most popular ones here. But I want to warn you at this stage that each one of them have serious concerns. And if you use them, please use them with caution. And here I want to present you with a specific case that is called permutation or perturbation-based interpretation methods. What does that mean? That means that because your black box models are too complex, you cannot understand as a human being. So this type of tools is just trying to use a simpler model to explain the more complex model. So in order to do that, they need to permutate your original data sets or create some artificial data points in the neighborhood surrounding your original data points. And then they build some simple models or doing some simple average to interpret that, because their model inherently cannot be interpreted. And because of this nature, these tools always need to, especially when the data points are dependent, they always need to create some artificial, unlikely data points in the feature space that relying on the predictions of that space. Later on, I'll give you more introductions on that space, on that part. So because of this, it causes that these tools could create misleading or biased interpretations. So this talk, we are going to focus on the permutation and perturbation-based interpretation models. Some of them are very popular in the industry now, like Shapley values or Sharp-based interpretation tools, Line, partial dependence plots, permutation-based feature importance. I'm sure that it's being used every day, widely in our industry. So now I want to give you some regulatory examples to show you why interpretation is important and why it's important when you use them for high-stake decision-making that you have to be very cautious. So here I list several examples from different countries, like Stanford in the US. They suggest the government to have some develop AI bills of rights that safeguards American public against powerful technologies, and interpretation is definitely written as one of the principles. And in Australia, we have our own AI ethics principle, and interpretation transparency is also one of them. And then in EU, we have GDPR, and there's a right to explanation. And recently, we have EU's AI Act, and they classify the different applications to high-risk, low-risk areas. For insurance, life insurance, health insurance are classified as high risk. So that means further interpretation requirements would be required for those type of applications. So we have to be aware of these potential regulations that's happening worldwide, and that is why understanding the potential vulnerability of interpretations in machine learning and AI models is very important, especially more and more companies are starting looking at using AI for important decision-making. And if you're working specifically in the insurance industry, here's another example that in the US, the National Association of Insurance Commissioners, they extend their white paper, which previously focusing on regulating GLM. Now they also say that for all companies who are using other black box models, you need to provide an interpretation. But what is written on their white paper is that, firstly, you need to get some plots describing the relationship between predictor and target variable. And you need to obtain a rational explanation for the observed relationship between each predictor variable and the target variable. So these are the insurance regulation. And in California, there is an automobile insurance regulation specifically saying that if you do automobile insurance business in California, you need to make sure that the top 3 most important rating factors are insurer's driving safety record, number of miles, and the number of years of driving experience. Make sure they are the top 3 and in this order. How can you guarantee this if you're using a black box model? Right? So these sort of examples warn us that we need some interpretations. How can we do that? So now we have the need, we have the regulations, we have the tools. Then the question is, can we use these tools to satisfy these requirements? Should we trust interpretations in machine learning? What do you think? So this paper is not the first paper. People have already been doing understanding the vulnerabilities of interpretation tools in machine learning for several years, but mainly starting from 2019 in recent years. So this is emerging research. So what I'm presenting is a frontier of this research that lots of papers have started looking at the adversarial attacks on different interpretation tools. And in particular, like in Rudin 2019 paper, they put it very specific that please do not use machine learning models or black box models for high-stake decision-making. That's almost their title. So people have different opinions, but I definitely agree with the message that if you do want to use machine learning, please understand these constraints and the limitations. OK, now let's look at one example, partial dependence plots. Apologize for the mathematical formula, but the key message is very simple. In order to compute a partial dependence plot, what you need to do is that you need to do some data permutation. So essentially, you need to, if you're interested in one variable, say age of the driver, then you need to replace that attributes with all the values that potentially you're interested and to the entire data set, and then compute the predicted values and average them. So this is what the formula is talking about. So for partial dependence plots, there are a very important assumption that many people are just ignored. That is, partial dependence plots assume that the features, your target feature, say age of the driver, is independent of all the other features in your data sets that you're using. If this assumption is not satisfied, then your results can be biased. So why it can be biased? Because if the features are independent, the PD plots would be based on extrapolations in the unlikely feature space. So if you change the age of the driver by an age, and then you have car type, you have all the other attributes. So this combination of the features may be unlikely to happen in the actual data feature space. But in order to compute the PD values, you do need to use those extrapolated unlikely values in order to get the results. Here is an example, what do I mean by extrapolation? Imagine that the x-axis is one of your attributes, and the y-axis is another of your attributes. So you can see that the data are highly dependent. And the extrapolation happens in all this blank area. So if you look at the red dots, that's one extrapolation point. In order to compute the PD plots, or the PD values, you need to use the value of the red dots, which is unlikely to happen in reality. So that's why the bias comes in. This is another example that your two features are highly correlated, positively highly correlated. So all these blank areas, so the data points only lie on the 45-degree line, but there are lots of blank areas in this graph. And the features, in order to compute the PD values, you need to, relying on values that actually happen in this unlikely space. Here I also draw two curves. If you look closely, the orange line, the vertical orange line, which has the legend says marginal distribution. So that's a marginal distribution of the x2 axis. So that is basically when you calculate the expected value for partial dependence, it's using this marginal distribution. However, if you look at the blue curve, which is a conditional distribution, conditional on x1 equals 50, then that's a heavy tail distribution. So that's another way to explain why there's a bias in PD values, because you're using the marginal distribution to compute the expectation, while the conditional distribution is actually very different. OK, then you may be curious. OK, I understand the potential vulnerability now. Then what could happen? This is a result that we have computed in our paper. This is based on the real insurance claims data sets. On the left-hand side is that before we do the adversarial attack, this is a plot that you would generate using your real data sets. On your right-hand side is a flat line. This is after the attack. So after we initiated the attack, I can give you a flat curve. So before the attack, it shows that, hey, this feature is very important. But after the attack, I can tell you, hey, the feature is not important. Imagine that the regulators say, age is a protected attribute. It should not be important for this decision-making. Then when you look at your plot, your data sets, you generate the left-hand side. But I can say, hey, use my model, and I can give you the right-hand side so that you satisfy the regulator's requirements. So basically, you tell me what you want, and I give you the partial dependence plot. So as long as the data, there's some dependence there, we can almost do that. That's what the adversarial attack means. And next, I want to show you how did I achieve this. Oh, before that, I just want to highlight why can we do that. There's the limitations of the partial dependence plots. Firstly, extrapolation. We just explained the extrapolation. Fail to account for the interaction effects among features, and it may yield misleading interpretation results when there's strong dependence. But there are some other ones like aggregation of heterogeneous effects. So if you got a flat curve of PD plots, it could mean that there's no significant influence, but it could also mean that different subsets of the data set exhibit opposing trends and they just offset each other. You don't really know what happened there if you just got a partial dependence curve. And also a third one is that it ignores the uncertainty. Okay, now I want to propose the adversarial attack. This is to imagine I'm a really bad actuary, so it's not proposed for you to use. I just want to look at, okay, how bad can I be to manipulate the partial dependence plots? So imagine that you are working on a pure predictive problem. You got your X, which is the data set, and you got your FX, which is your model, right? So FX is your black box model. What I wanted you, so if you come to me and say, hey, Faye, can you give me another model that I can manipulate my partial dependence plots? Then the AX is the model I'll say, hey, I give this to you. Just replace that with your FX, and you can get whatever PD plots you want while maintaining the prediction accuracy for your FX. How can we achieve that? So you can see in the formula, in addition to FX, we got two additional functions, CX and GX. CX is basically a classifier. It gives you 0 or 1 to just to differentiate between the instances from the original feature space. That's the likely data points. And those from the extrapolation domain, those unlikely data points. So if CX equals 0, that means, oh, this data is from the original feature space, I'll give you FX. If CX is 1, that means it's from the extrapolation space, I'll say, use my GX to compensate your outputs, because you don't have any data on the extrapolation space anyway. So if you don't use GX, what you will be using is the predicted value of X. It's basically unlikely points anyway. So just use my GX, and let's work out what partial dependence plots you want it to be. So this is the picture, just explaining how this framework works. So you got your original training data. In order to compute a PD plot, you need to permute your data sets, permute each of the attributes that you are interested. And then we'll feed that into my classifier CX. So the classifier will determine, okay, in the permuted data sets, is this from the true feature space or from the extrapolation unlikely space? If it's from the true space, go to FX, give you your predicted FX that you originally want. If it's from the unlikely space, I'll give you my GX. That's what I designed to satisfy your requirements, what kinds of PD plots that you want. So GX would be purely depends on the PD plot in your mind. Do you want your age to be important or non-important? Do you want it to increase or decrease? Just tell me what you want. I'll give you the reverse engine, what the GX should look like, and give you the PD plots that you want. And here is just some easy things to think about. How can we design a classifier CX? So it's basically just some independently generated uniform distribution so that it can cover the entire space, including the the extrapolation space. So in order for CX to work, we actually have to incorporate or self-generate lots of augmenting data points so that it can occupy those unlikely space. They will play a very important role to generate the full PD plots. And then how to construct GX, as I said, in order to construct GX, we need your desired PD plots in your mind, and I can reverse engine to tell you what GX should look like so that you can generate the plots you want. So PD plots is basically a tool to help you understand if I change one variable, what's the other variable change. For example, I'll tell you the example later. So in this framework, we can also for multiple PD plots at the same time. Right, so previously, it's just one PD plot. If you say, OK, I want to look at the PD plots of driver's age and gender, and then I can give you a model that for 2 PD plots at the same time. Or if you want more, this can be easily generalized for multiple PD plots. Now let's look at the empirical result, and I'll show you what's the implications for business. So here we got some real data sets from an open source, which is a French claims data set. And dependent variable, we assume we are building a frequency model, number of claims. And in the data set, we have 14 features. And let's focus on 2 variables, driver's age and vehicle values. We look at these 2 because both of them have some dependency structure with the other variables so that we can play. So that means they do not satisfy the independence assumption of PD plots. So here are some scatter plots to help you understand that they are highly correlated. This is another graph to show that the holistic correlation picture of the different attributes. The highlighted ones are the focal variables I want to get explanations for. OK, let's go back to the plots again that I will show you earlier. After applying the adversarial model structure that I just showed you, we can see that before and after attack. So before attack, you can explain it as if I change the value of my age, how would my prediction change on average? So you can see there's significant correlation between age and the predicted value, the number of claims. On the right-hand side, after the attack, you can see that there's no relationship. And all I change is your model. You use fx, I give you ax. That's it. I did not use any additional data sources. All I want is your model, your data, and what PD plots you want. This is another example that the second variable we're interested in vehicle value. So before and after attack, similarly, before it's an important variable, after it's an insignificant variable. Of course, in this framework, we have 2 goals. One is that we want to generate fake PD plots. The other one is that we want to predict your original predictions. So these 2 goals, there are some conflicting interests of these 2 goals that can't be satisfied at the same time to the best that you can. So there's some trade-off you need to make. So I created 2 measures to understand to what extent can we, on the one hand, maintain the prediction accuracy of the data sets we are interested, that is our original features. On the other hand, is how accurate can I do the attack? So again, this is based on pure real insurance data sets. So let's just focus on the right-hand plot, which is easier to understand. The left-hand is just a 5-fold out-of-sample validation, just to make sure that the result is robust. On the right-hand side, we can see that the different values on the plots show that that's basically different threshold for the classifier CX. So the different values indicates that the model would perform better and better if you increase this threshold, and the accuracy will be improved. However, we can see that even in the worst case in terms of prediction, in terms of the attack, so in the worst case scenario, that say I basically assign as many real observations to my real data points to make sure that my fx perform as good as possible. Even in that case, the accuracy of the attack is actually not too bad. It's around maybe 0.95%. And in another extreme scenario, if I want to make sure that my attack to be as good as possible, make sure that the curve is exactly close to what I want in my mind, then how about the accuracy? How much accuracy can you maintain for your prediction FX? So on the x-axis towards the left-hand side, we can see that in the worst case, the prediction accuracy is around 99.4%. This is the worst case. So that means even in the worst case, we only need to use 0.6% of your real data to satisfy your need to do the attack. So all I want to say is that in order to initiate and make sure that attack works, we only need 0.6% of the real data to do that. All the remaining 99.4% data are the original FX that we don't touch at all. So this indicates the power of this attack. Only use a very small amounts of real data. You can change the PD plots significantly. And another example is just do some simulation. I would just want to present you with another example that say maybe you wanted the opposite case, that is you want to look at if originally my feature is insignificant, for example, on the left-hand side of the plot, and I want to make it significant, I want to increase, you can also do that. As long as you tell me what you want, this adversarial framework could potentially help you with that. So this is just uncovers how vulnerable the partial dependence plots can be. Okay, now, the last several minutes is, okay, I tell you the story that I can manipulate your PD plots, and I do not need any further information, and I just need what you want. So what's the implication for our business and for the regulators? So there are basically three ways to use AI models. One way is that you don't use it, and you just turn to the traditional statistical models. The second way is that you use a hybrid approach, that you use the black box models just to do feature engineering or maybe just data exploration. When it comes to the business decision making, you turn to the more interpretable, simple models. That's another one. The third one is you go one step forward to implement black box models for your business, use that for business decision making, but you can't explain it. And then you supplement that with some interpretation tools, like partial dependence plots, SHAP, or LIME. So it's a third point I want to draw your attention. Please be careful using the third step. I want to call for two things. The first one is that for the third strategy, I would recommend only use that for low-stake decision-making because of the vulnerability of the interpretation tools. And if you do want to use that, please check, does your data set satisfy the assumptions, the independence assumptions, and also the potential bias it could create? Are you interpreting the results in the right way? There have already been examples showing that using these AI tools for very important, say, healthcare decision-making cause significant harms. And the second call I want to say, is there real value added using AI? On the one hand, I definitely echo that we should look at AI, use AI to boost your business. However, for some of these applications, if you are only looking at a very small structured tabular data set, do you need neural networks? And do you want to improve 3% prediction accuracy, which is also not guaranteed? If you change your seed, it may change as well, but you lose the entire interpretability. What is the real value added in applying AI? So that's the second point I want to mention. But for some other low-stake decision-making, AI can do a very good job, boost your business, save your time. It can do lots of good things. But when it comes to high-stake decision-making, please be cautious. And then finally, I want to say, how can we mitigate the adversarial attacks on PD plots? One thing is that you can complement the PD plots with some additional interpretation tools. Here I say the ICE plot is another example. this is the ICE plot. It's basically individual plots. When you average out these individual plots, it goes to PD plots. So it's an individual version of the PD plots. So if you look at this, you can clearly see that the right-hand side has something wrong with it because there are some weird curves that are inconsistent with the other data plots. So this actually can give you a warning that there's something wrong happening there. So complement the PD plots with some other tools can potentially be helpful. And also assess the dependency before using that. Maybe use traditional models if the AI model does not give you, value added, or you can adopt a hybrid approach. So I think I want to stop here and leave the remaining 10 minutes for questions. Thank you.
Thanks, Faye, for that very interesting paper and presentation. I'd just like to encourage anyone, if you'd like to enter. We've got a couple of questions coming in already, but please feel free to put more in. Maybe just to get started on a less technical question around, can you give us an example of a practical application within the insurance industry of where you might see what you classify as a low-risk application?
Yeah, I think I guess many of you have better understanding of what potentially can be classified as low stake. I mean, if the application does not directly facing the customers, I think that maybe, for example, you just use that to help understand some of the business that's not particularly customer relevant. It's basically, does it affect the people's lives directly? I think that's my understanding of the high stake. Yeah.
Mm-hmm, mm-hmm. Okay, thank you. And with the potential flaws in these interpretation tools, how do you see the future development of these tools to enhance their security and reliability?
Yeah, I think at the current stage, the technology haven't evolved to the stage that we can, on the one hand, use all these complex models, on the other hand, we give you perfect interpretation. This area is still evolving. Lots of the current models are looking at even causal-related interpretation, because that's going to be even more helpful. So almost all the existing models are association-based. You only know that these attributes are associated with your response. But is there really a causal relationship or just a spurious correlation? We don't know, right? So interpretation is definitely an emerging and a hot topic in the academia. But at the current stage, all the state-of-the-art tools I can see, every single one has their limitations. If you use them, check what are the assumptions there. Can your data set satisfy those assumptions?
And you spoke a lot about the partial dependence plots. Are there any other alternative interpretation methods that you think are less vulnerable to these attacks?
Yes, so today's talk mainly focused on the permutation-based tools. So this applies to partial dependence, permutation-based feature importance, Shapley values, kernel Shap, Lime. It all applies to this type of models. But there are some other interpretations that do not rely on permutation. So for those tools not relying on permutation, at least some of them are not. So they are not vulnerable to this type of adversarial attacks. But they have their other limitations. So it has to be a case-by-case interpretation tool. Even for the single, I would say, okay, even you say I do not use machine learning models, I want to just use my traditional GLM. GLM also have its constraints. Because if you want to interpret your GLM, you interpret the beta. And if you want to interpret your beta, you have to say, assume that all the other attributes hold constant. And then that's how you interpret the beta. So it's still a partial interpretation, because it can all still be, it's still not the holistic picture. You may still interpret it in a unlikely way. So I would say every single model has its limitation. And it's just that when you use that, you need to understand that.
Okay, and I think that probably partially answers another question around what are there any other tools you would recommend other than the partial dependence plots? But I think I hear what you're saying is that every tool has its limitations.
Exactly. So what I want to recommend is that think about what is your application. If your application is too important, and then using those black box models can be dangerous. So it's just, I would say, for those low-stake applications, it's probably easy. I mean, one example of low-stake decision-making is like maybe Google Translation. We don't really care about how the translation is done, and it doesn't matter if there's a wrong translation, right? So this sort of applications is okay. It's definitely usable. But if you are judging whether these people should be, it's a criminal justice or financial decision-making, it's really very important for individuals' life, then I would recommend have really serious thinking about which model you are using, and can you interpret that?
And there's another question that's come in around, by demonstrating that these partial dependence plots can be tricked by these adversarial attacks, does that mean that they're biased in the first place?
Exactly, that's a good question. Even you do not apply the adversarial attacks, say my left-hand side plots, the original partial dependence plots, it can still be biased. If your data sets are dependent, you can also not rely on the left-hand side plot, because those values are based on using those data predictions, extrapolations in those unlikely space, and averaging out all the data points there. It's still biased.
And are you able to share any measures that can be implemented to detect or mitigate the effects of these adversarial attacks on machine learning?
Yeah, sure. So one thing is, like I mentioned, I recommend that if you use interpretation tools, use multiple of them. Don't just rely on one of them. Because if you use multiple, then you reduce your risks. Because every tool has its own limitation, but the limitations are not the same. So you sort of reduce the risk, use multiple tools. That's one way. Another way is check your data set. Say, partial dependence assume independence. Does your data satisfy that? Check your data set in the first place to check whether it satisfies those requirements.
I've probably got time for one or two more questions. What if the important relationships between the variables that enforce fairness of pricing are embedded in neural nets? And do you still see this as a risky black box?
Sorry, can you repeat the question
neural
again?
Nets, maybe neural networks?
Neural nets, yeah.
What if the important relationship between the variables that enforce fairness of pricing are embedded in the neural nets?
Yeah, neural nets is one of those black box models. It could be. I mean, for example, if the regulations say race or gender is a protected attribute, and you do not directly use them, but you use many others, and I mean that could potentially impose a proxy discrimination. It's not guaranteed, but there's some risks of having that potential discrimination fairness issues there. So it's not just specific to neural network, any model would face this risk as well.
Thanks. And maybe one question just to wrap up. I guess a lot of the people in the room here work primarily in the areas where you would classify as high risk. We deal with high risk decision making and data sets. What's the one thing that you would like people to take away to think about when they go back to their desk next week?
Yeah, maybe I can 2 points. One is look at your data set. Are you dealing with unstructured, big, complex data sets? What is the value added applying AI machine learning? Do you really get the value? Does the data set really fit for the big neural network? And secondly, what kinds of application, what kinds of requirement do you need for the model? And there's always the fit between what you want and what the data sets present. So you need to have a good fit between data and the model, and also make sure that you satisfy all the requirements. So basically, have a fit-for-purpose model for the data sets for the stakeholders.
Okay. Thank you. We're just about out of time, so please join me in thanking Faye for the interesting presentation today.
Thanks, Kirsty. Thank you, everyone.